Okay. This is starting in 5 minutes. Here is your other one. Let me change the camera shots. Okay. Momentarily. You can have that if you'd like. That's really up to whoever wants to be the highest here.
So who's going to take the high chair?
That is the question.
Feet won't touch the ground. I'll fall off.
I think the moderator should take the high chair.
Would you guys want a table in front of you? You're welcome to take it. It's really up to you. It's not going to go in front of. Okay.
We can have a table
At least we have
awkwardly in the middle. That's fine.
You are live?
You are live.
As far away from us as possible.
So that far chair is a
We're
little
sitting.
too far. You want to maybe cheat everybody a little bit towards me.
No.
Everybody can cheat a little towards me.
You want to make sure the
You can see yourselves in the shot right there. You can see where the chairs are. Okay.
We're good.
We're still setting up, everyone. A few seconds and we'll start. Okay, so I have a mic. I have both mics. I'll distribute the other one and take it away if necessary. I think this is going to be fun. So, hi everybody. We're going to start with a round of introduction. So this is the Graph Data Science panel, and we are going to start with a round of introduction. So go ahead.
Yeah, hi, everybody. My name is Jayu. I'm the VP for Product Innovation at TigerGraph. And my background is also, I got a PhD in core database technology focused on relational parallel database engine. And then through long story short, I actually went to Teradata, went to some startup, and finally, before I joined TigerGraph, I was at Intuit for 18.5 years, focused on enterprise data architecture and strategy. And that's where I discovered TigerGraph. So 8 months ago, I decided to join TigerGraph to really evangelize Graph for everybody. So that's my introduction.
Awesome. So I'm Alicia Frame. I'm the Senior Director of Product Management at Neo4j for Graph Data Science. My background is I actually have a PhD in computational biology, and I spent the first 10 years of my career basically doing data science on graphs for risk assessment and drug discovery. I joined Neo4j just over 3 years ago, and I joke that it's to put myself out of any future job, but really to translate bespoke models that I was building for specific customers, employers into a platform that any data scientist can pick up to start making sense of graph. And so work on the Graph Data Science Library and Aura DS.
Thank you. Well, my name is Giuseppe Futia, and I'm currently Senior Data Scientist at GraphAware. And my main responsibility in GraphAware is to incorporate graph representation learning and natural language processing features within our product. I have a computer engineering background, and I have a PhD from the Polytechnic University of Turin in Italy, in which I try to identify some interesting techniques for the automatic building of knowledge graphs from heterogeneous data sources. And I will try to exploit also graph-based machine learning techniques in order to perform this specific task.
Hi, my name is Shauri Das. I just presented. So I'm actually working for Oracle. Started sometime in the last century. I don't remember exactly when. I did my PhD from Rutgers, before that master's in Vanderbilt, and then bachelor's at IIT Kharagpur in India. And I used to work in AI initially when I started my work, but then AI got into this winter AI winter kind of thing. And so before that, I was working in knowledge-based design and expert systems in the OPS 83, all those things for production rules, production systems, inference, and so on. But then I moved to communication and paradigms and synchronization, did my PhD in that. Then I joined Oracle, and as the database core layer, I used to do the, all kinds of concurrency control and all those things in the Oracle kernel, actually. And but in 2002, when the RDF was starting up, at that time I got interested in RDF, and I kind of took the initiative to start the effort on graph databases, RDF at that time at Oracle, and it's doing pretty well. I'm happy about that. There are lots of course, very talented people in our team and the group, and we hope to basically get people to see and use graph databases when it's appropriate. Again, one thing though, I don't think graph is the only thing that is every data. This is my sense. Every piece of data, right, can be represented in different way. It depends upon what you are looking for it in there, right? We do whatever we want underneath. That's fine.
Great, thank you, Suri. So maybe we're here for another 50 minutes or so. Let's see what we're going to discuss. We're going to discuss graph data science, obviously. Maybe try a definition to start. And then we're going to see what does graph data science brings to knowledge graphs, and what do knowledge graph bring to graph data science. And we're also finally going to look at the future maybe of graph data science, and does it go through knowledge graphs? So without further ado, I would like to ask you, Alicia, what is your definition of graph data science?
So I probably will have the simplest definition of anyone on the panel. And when someone says, what's graph data science? It's just doing data science with connected data and using the relationships between your data points as additional information, using those to make sense of your data. So if you're running queries on a knowledge graph to answer a question, that's graph data science. If you're running graph algorithms to figure out what's most important or what's similar, also graph data science. And if you are doing graph neural networks, graph embeddings, advanced machine learning, still graph data science. Graph data science is just answering questions with connected data.
Thank you. How about you, Jay?
Yeah, in this case, I totally agree with Alicia. But anyhow, as the name suggests, it's about adding graph to data science. And then, as you know, I think this is the trend. I want to actually amplify this. Is graph plus ML is the future of AI. Remember that. And that's what graph data science is really about. How do we connect, the power of graph or graph database, knowledge graph, actually has a lot of, human intelligence built in, combined with this black box machine learning. How do we make sure they work together so that we can achieve a level of, accuracy, recall, rely on black box magic we'll never get to. So that's my definition of graph data science.
Great, thank you. Yes, we can continue with Giuseppe if you want to complete a little bit the definitions.
Actually, both Jay and Alicia cover, I think, the main features of graph data science, so it's not an easy task. But anyway, I think that in the case of relationship, actually we can consider it as a sort of a new additional dimension that we can exploit within data science. But in another case, the graph is the unique data representation that can we use for describing specific phenomena and specific business use cases. Because if, for instance, if we consider examples such as fraud detection within economical transactions or other type of operations, this is just a collection of data points that and the graph represent the unique way in order to describe this type of data. And the same thing happens, for instance, for the logistics chain optimization. And this is another example in which we need the graph for describing the data. Because if we don't use a graph, we have just a flat representation of the information that it's not useful in order to perform analytics and specific analysis in order to detect patterns, for instance, within the data. So I think that the graph add a new dimension in multiple cases, but for other cases is the unique way to represent data.
pretty difficult to do after 3 persons, to pretty much give the correct answer. So the only thing I would like to add is that the data items don't live and are not the isolated stuff, right? They're all related somehow. Okay, and so the graph way of viewing the data allows us to see that very clearly, cleanly, simply, and then our workload can then actually take advantage of that thing that we're projecting to the user, right? So the data does not change when you represent something as a graph. The data is there. It is connected, right? We are all connected. I'm connected to my mother. I'm connected to my father, right? It's just that the graph way of visualizing the thing, right, or viewing the thing in user's mental head makes it much easier for them to think about the connections, right, as opposed to that being hidden in some other data structures, right? So that's basically, I think, the main idea of graph. It makes it easier for one to think in those terms, write their programs to do the interconnections and so on.
Great, and keep the mic, sorry. Yeah, why? So here we're looking at knowledge graphs in this conference. We hear about knowledge graphs everywhere, and we're seeing use cases, application of knowledge graph. Why are knowledge graphs used? Data governance, data integration, and other and many other applications. Now, so when building knowledge graphs, when maintaining knowledge graphs, how can graph data science help to create and have a usage of better knowledge graphs? So go ahead.
Okay. So if I understand the question, like, it's basically you're saying that how can we improve the knowledge graph
using graph data science? And if you want to discuss applications, certain use cases, for example, or if you want to discuss specific techniques that you think are useful, your choice.
Yeah. Let me keep it as a general discussion. So the point is, anytime, right? Anytime we are getting more information about the domain that you have, right? It obviously helps if the implementation, if that extra information is represented in a way that people like to see it that way, right? It should not be hidden in our data structures. I can take something and the same data, I can write it in as C data structures, and not many people will like that, except maybe some developers, right? So if we get extra information from machine learning, we want that to be reflected in the knowledge graph that we have as an augmenting that one, right? And that is going to be very useful because the users will see it directly at that point, right? So.
Yeah, and I think that actually, Francois, your second and your third question describe the bidirectional connection between graph data science and knowledge graph, because on the one side, we can exploit graph data science and machine learning techniques to build, enrich, or refine knowledge graphs. But on the other side, we can exploit knowledge graphs to feed automatic systems that make, for instance, intelligent behavioral decisions. And in regards to the first side, I think that the typical techniques that we can apply to build a knowledge graph depends on the original source. Because, for instance, if in the case of textual contents, we can apply techniques like named entity recognition that allows you to identify, for instance, named entities in the text. And if we consider the healthcare domain, we should be able to identify diseases, drugs, proteins, or genes. But in many cases, this is not enough, right? Because if we consider, and actually I will discuss also tomorrow, if we consider a mention like diabetes, well, actually there are multiple diseases that can be connected to diabetes, like type 1 diabetes or type 2 diabetes, or also gestational diabetes. So basically, we should be able to disambiguate between these named entities in order to identify the entities that are located in a specific reference knowledge. But this is not enough, because we have to be able to extract the relationships from the text in order to reach a structured representation of your knowledge within contextual context. We can extract information actually from semi-structured sources, from JSON files, CSV, XML files. And here there is a concept that is really familiar to the RDF community. This is called mapping. So basically, we have to identify a connection between the local schema of the original source, so for instance, the fields of your CSV files, and the global schema represented by the ontology, we should define the, let me say, the description of the domain from an high-level point of view. And this is also another task, has the extraction from the natural language processing. So there are a lot of techniques that we can perform. Each techniques depend from the initial source. And so building knowledge graphs is still a research activity that requires, I think, applications in industry, but also basic research from academia.
So I guess this is kind of I love this question because it's the opposite of the direction I usually think of it in. But I think Giuseppe did a really good job of kind of breaking it into building your graph and then enriching your graph. And I also think about evaluating quality control for your graph. And so graph data science includes, the NLP that you might use to build your graph in the first place, extracting subject verb object relationships so you have a knowledge graph. Also creating a graph from maybe non-graph data, like maybe I have image embeddings, maybe I have text embeddings. I can build a k-nearest neighbors graph to represent that, tie that to other data in my knowledge graph, populate it. But then once you've got your knowledge graph, I think you have these two questions. One is this right? Is this good? And the other one is it complete? And I think graph data science also helps in kind of those two steps of building out your knowledge graph. So simple unsupervised techniques like graph algorithms can help you evaluate, okay, I created a knowledge graph. Is this right? Is this real? I've done this before in my life where you've got a great NLP pipeline. You're so proud of your knowledge graph. You start running models on it and you're like, these are terrible. Something is horribly wrong. And simple graph algorithms like degree centrality can start to point at, I have corrupted data. I joined something wrong when I built it. And so it's really important we don't forget the role of graph data science in evaluating that new graph. And then once I have a graph, is it complete? I know there's a whole track at this conference around GNNs. Really popular area of research is knowledge graph completion. So I've done some NLP on my text. I've built a knowledge graph. What's missing? Can I fill in any information just based on the graph itself to fill in the blanks? Where am I missing labels? Where am I missing relationships that should be there but weren't detected? And techniques like graph embeddings, graph neural networks, node classification, link prediction, all help you kind of complete that graph that you've started building. And so I think breaking it into those stages of building, evaluating, and completing is a really nice holistic way of thinking about how graph data science builds into your graph creation process.
Wow, how do I follow that?
So let me try
My best. I think I share the same thing. So the way I look at the following, if you think about on the left-hand side is the knowledge graph, and very likely bootstrapped by human knowledge, right? You want an ontology, you want to have knowledge representation, and you want to feel some data there. So there is a notion of how do you bootstrap the knowledge graph, which is the view. And that itself has some machine learning element. I think you already, NLP extraction, all these things. And the other side is, what is the purpose of the knowledge graph? It has to be used by people. The question is this knowledge graph complete? Is there room for improvement, enrichment? Guess what? Then machine learning plays a role. Right? You use graph-based feature extraction to enrich your machine learning model. What's the result of machine learning? New insight people cannot do. That's what machine learning is about. If you already think about rule, there's no need for machine learning. Machine can somehow magically figure out those hidden relationships human are not aware. When you have that result, then you want to feed back to your knowledge graph. That's how you enrich it. Now, you actually adding basically hidden relation become more explicit. You add human knowledge to it. Then your knowledge graph becomes richer and richer. And that's actually a virtuous cycle. That's how I look at it. That's why I'm so passionate about, knowledge graph or graph, superset of knowledge graph, or we can say knowledge graph is everything, and machine learning. That's actually the ultimate goal of hybrid AI. We focus a lot about knowledge graph, machine learning, but take a step back, hybrid AI, right? Rule-based human intelligence, we have a system to do that. Knowledge graph ontology is one way for us to model the world, to map the data. The other side is really the new AI, right? Which is rely on, unbelievable, compute and processing. How can we combine those two together? I think graph data science is the cornerstone to connect those sites together.
So yeah, thank you, Jay. You gave me a segue there, talking about rules. Because until now we talked about knowledge graphs as graphs, and we haven't made a big distinction between a knowledge graph and a graph in general. And you mentioned rules in terms of business rules, and we're discussing here, we also have a track on ontology, right? I think these are the two ends of the spectrum at this conference, right? The ontology and modeling track and the GNN track on the other hand, right? So one is really modeling oriented, the other one is statistical analysis, etc. So how does the ontology, the schema, how do the business rules play in that game? What is the status of using those for graph data science, and what is the future if you have an idea? And I would like to start maybe with Suri again.
Really? Why do you always put me
Sorry, you can have it after.
So I thought you were going to start from there, so I was not listening to you.
Right. So then the question is, can human being always express the rules? Can we always write Sparkle queries to express everything we want? Sparkle queries has its own limit, right? That's why today, relational AI, what's it, Mike? Bob talked about, which is a trend, is convergence of analytics, graph, and also machine learning in the form of language, convergence of procedure and declarative. That's why it's so important. For me, rule is part of the knowledge, right? We cannot separate that. How does graph data science support that? I think that's, for me, it's the same thing. There's certain rules can be expressed by human being. The certain rules may not be. You have to rely on machine learning, somehow magically learn some of the patterns. And then when you look at those patterns, say, how do I incorporate in my rules so that I can enrich the overall knowledge? That's my point.
So I think this is an interesting one, and I actually agree that you can't have one without the other. I feel like I have a foot in both worlds. In my postdoc, I actually worked on ontologies for environmental exposure information. So like firmly in that world of defining rules, hierarchies, how things are related. And then for most of my career, I've sat in the GNN space where it's let the AI figure it out. But I think when you have one without the other, you lose the signal. So I can say when I spent over a year in a conference room defining an ontology, we didn't ever do anything with that ontology. We came up with a great ontology and we said it's out there, people can use it, but we never gained any insight from it. In one of my previous roles, I was working in drug discovery, identifying new gene targets. And we had a schema-free database at the time, and we were just chucking information in there. We found this, the NLP spit this out. Now we're going to run some GNNs on it and see what comes out. And we had great predictions like water might be a treatment for cancer. Thank you for that prediction. And I sat there and it was like, what's wrong with the AI? What's wrong with the AI? And I said, oh, it's not the AI. It's that we have no constraints on what's going in here. We have no rules about what can be connected to what, or what counts as a chemical, what counts as a disease. And if you don't have rules, and if you don't have data science, you don't have the full picture. And so like when I think about just simple graph data science techniques, from the beginning, you're thinking about, can I use this algorithm? Well, what kind of graph do I have? Is it monopartite or is it heterogeneous? That's a rule. Do I have one node type, multiple node types? When you're choosing a technique in the GNN space, you have to choose a technique and decide, am I going to consider different relationship types? Am I going to consider multiple labels? What are the properties I'm encoding? Those are all rules. So I feel like maybe there's this made up beef in the community of like, ontology, RDF people hate labeled property graph people, hate GNN people. But I really feel like it's a better together story. You need rules to make sense of your data. You need graph data science to process all that data that you've generated with your rules.
Yeah, I think that both Jay and Alicia get the point, right? We need graph, structure, information, and we need knowledge incorporating into this knowledge, into this graph. The current problem, I think, and here's a question that comes to my mind sometimes, is that, but the current graph data science techniques are able to learn the knowledge in the way in which we consider knowledge. Because I would like to make these examples. Consider, I'm just taking my running example than before, we have this sort of very rich knowledge graph in which we have drugs, diseases, genes, proteins. We have a lot of multiple relationships between these nodes because to a disease is associated to a specific gene, which encodes a specific protein, and a drug can be used to treat this disease. And on this knowledge graph, we can perform a lot of stuff. We can perform specific analysis like shortest path between nodes, computing between centrality, perform knowledge graph embeddings, apply graph neural networks in order to node classification, link prediction, a lot of stuff. But if we change the labels of this graph and we attach no meaningful stuff like numbers, so this is the node 1, this is the relationship 1 or relationship 2, etc., then we can perform the same things. We can perform graph neural networks, we can perform knowledge graph embeddings, we can apply shortest path. The current problem, in my personal opinion, is that current machine learning techniques are not able to encode the knowledge, because if this graph represents something or something else, it's the same. Because we can apply the same techniques, but we do not have notion of knowledge when we apply these techniques. We should have as human being, so we can select, let me say, a specific direction, but the machine is not able to understand this stuff. It just sees different type of nodes and different type of relationships. So I think that there is a lot of space, a lot of room in order to identify the way to incorporate the knowledge conveyed by a knowledge graph into this type of techniques. That's my opinion on that.
It actually gets harder after all three of them. I think I agree a lot with what particularly Jay said about that rules and the ability to infer new information from what you have, right, is extremely important. And because the thing is that if it is hidden in your data, the users are not seeing it, and that doesn't help them. They are not going to do that deep thinking, right? So which way the new data is coming up is really none of the concern of the user that is looking at it, whether it's coming from logical inference through rules and ontology and based inference is perfectly fine, or whether it's coming via machine learning, and that's perfectly fine too. One disadvantage I see with the derived facts that come from AI or machine learning is the explainability aspect. Sometimes it comes up saying, oh, yeah, the user says, how did this arrive, right? So the explainability aspect, I think there's more to do in that one to really make it helpful for the user, not get them completely confounded by it. So that's what I think is something that we need to pay more attention to.
Does anyone want to react to the explainability aspect? Anything to add there? I've seen reactions.
I absolutely agree with this point, and I think that the old school of knowledge graphs, so basically coming from the expert systems and performing some reasoning and etc., could be one of the possible answers to the explainability, because using the reasoning, we are able to inject a bit of knowledge in the algorithm. So basically, I think that it could be the good direction. There is a lot of space, but a lot of stuff to do, because I think that the way in which we can exploit this reasoning part within graph machine learning or knowledge graph embedding techniques, I think that there is no best practice to do that. And so I think we should go in this direction. So identifying best practices and approaches in order to combine in a really concrete and effective way this type of information.
I think when you talk about explainability with machine learning in general, like often explainability is one of the first and foremost concerns people have, whether it's graph data science or regular data science. And I think one of the biggest reasons to have a knowledge graph is explainability. And I've worked on projects where you have domain experts and you can build advanced models or you can run queries. And both of those are just as valuable. One of them is finding the information that you think should be there. And because you're a domain expert, you can craft that. You don't need a machine learning model. When you're doing machine learning, it's often you need to go back to what were the rules that built this graph? What was the information that went into this graph in order to evaluate, does this make sense? Or if I just learned some weird artifact of my graph architecture? And I think explainable GNNs, explainable AI is such a major area of research, but it's really hard. So if anyone in this room has ever trained a GNN, it's slow, it takes a while. When you start looking at explainability methods where you're maybe doing knock one out perturbation or looking at things like PageRank of individual nodes that go into your attention mechanism, that makes it even slower. And so you have this kind of trade-off between getting results quickly, innovating, improving on what you're doing, or trying to add explainability back in post hoc. And I think having that underpinning of, I trust my data, rules went into this, I can look at my predictions in context, is a really powerful tool that you can use in addition to these cutting edge techniques for explainability. So it's very much like a full life cycle thing.
Yeah, totally agree. I think I'm glad we all agree. We don't have any controversial. So,
Yes, this one.
knowledge graph is very visual. Right. I think that's the beauty, and then very easily recognized by human being. We suspect our brain functioning like this. The famous phrase called connecting the dots. What is connecting the dots? That's a graph. And that leads to high level abstraction, patterns, context, right? So with that, if you organize those data, connected data through a graph, after you're running machine learning, you can easily visualize those. You can actually, even with somebody easily look at this. For example, we have an example. Microsoft Xbox actually used TigerGraph to do community detection on 100 million gamers. What they're trying to do is figure out how these gamers interact with each other, what is active community, they want to grow and nurture, and then also making sure, of course, those gamers will spend more time, will interact, much better experience, right, engagement. But what they did is just run a famous algorithm called Levine graph algorithm. By the way, that's machine learning. And we're able to run that algorithm push down into our database layer, become almost like a stored procedure. One single command, you just run that. Result, there's a result. How do you know it's right or wrong? The minute they bring up visualization, they immediately see, yeah, these guys actually interact a lot with each other. So that's actually one example is when you actually add a graph to your machine learning, suddenly it's a lot more visible and more understandable by human being. And that gives you a lot of advantage in terms of explainability.
Great. Often it's very interesting. again, give me a segue. It is great. From one side to the other, like the questions are coming. Often when you speak about graph to someone who doesn't know about graph, they will say, "Oh yeah, visualize this. Oh, graph. It's you're drawing things. That's what you're doing." So that's interesting. Is there something you guys would like to add about visualization and how the process helps? Visualization help explaining results.
That was very great. Now I'm kind of not sure whether I'm going to do that next. Visualization is absolutely the most important thing, I think, because you present the data in a file. Doesn't help the user who is looking at it. The data science user or is some user who is not familiar with the data structures and so on underneath, right? They really want to see it visually. And not only, I would say that not only just a static visualization. Ideally, if we did something, if we could show that as an animation, right, that is even more helpful. So I completely agree, or at least that's my opinion, is that visualization has to be part of any thing that we offer to the user community. Yeah.
And so the relational world brought us Tableau and Power BI. What is there room for disruption here?
So Neo4j has Bloom, which is like our purpose-built visualization platform.
No sales pitch. You define it.
I would say also TigerGraph has Graph Studio. Like, it's super important to be able to visualize your graph. And the problem with putting graph into Tableau is Tableau isn't really built for graph. And I have spent painful hours of my life trying to build plugins for Tableau that can do little bitty graph visualizations. But if anyone in this room has used Gephi and cried, graph visualization is hard. But you can't really do graph data science without visualization, both from kind of the exploratory perspective, but also the communicating to your customers, collaborators, teammates perspective, right? If you're like, cool, I did this knowledge graph thing, you just have to believe me, it's magic. Here are the files. They're like, what have you been doing for the last 3 months? Having a visualization where you can show these are the communities that I found color-coded, or here's the shortest path between this warehouse and this distribution center. And I can show you visually as nodes and relationships is super powerful. And I think when you talk about, is there room for disruption? I think it's been disrupted, right? Like, all of us here work on tools to visualize graph data because tables just don't do it, right? 2 dimensions, maybe like a heat map in a matrix. We want to see the connections. You want to see those insights in real time in visualization tools. And you want to make it easy. You don't want to tell people, here's the instruction manual. I hope you like JavaScript. Good luck. So it's all about, enabling people to make sense of their data.
Great.
Can I add on that? Wow, we have a lot of in common. Thank you. But this actually reflect, right? We actually went to the, we have a lot of customers, as well. That's where you learn from a customer. When they actually turn their head, because a lot of customers, sometimes they don't know about graph. They know about relational. The minute they see the visualization, they just say, whoa, I never think of my data this way. Right? And then, because they're so ingrained in relational, the columns, rows, I call them 2D data. Graph give you multi-dimensionality. You're not constrained by 2D. You can connect as many as you want. You don't need to rely on joins, binary joins, just like today relational, right? So with that underneath it, you can imagine there's a 3D visualization. You can explore any dimension you want, right? This is where we are, like Neo4j, we are providing connectors. Our customers tell us, connectors is great, but you actually reverse ETL back to the relational view. Well, sometimes certain insight is okay. You want to do aggregation, sales by region stuff. That's common stuff. We can do it as well. But what they cannot do is see the additional graph relationship. So there's a customer working with us say, can you add a add-on component to my Tableau or Power BI to show the graph view. This shows graph, give you insights. None of those BI tools can give you. Right? So the world is not about we want to replace BI. Can we enhance BI? Can we provide a level of higher degree of dimensionality, more insight? And that's where people actually find value. We're not saying we want to replace relational technology. It's going to exist forever. Just like it today, right? But what we can do is show you the additional value graph bring to the table. I think that's all of us have to think about that. Sometimes we're being too idealistic. Oh, this technology is going to replace it. No, people already have a lot of investment there. We want to protect you. Whatever the insight you get is good enough, good enough. But are you missing any deeper insight? Can we bring you that graph dimension? Can we show you how they're related? Can we help you get your machine learning much accurate? That's how value proposition.
Thank you. I think Giuseppe also wanted to react.
Just a small comments. I think it's in a data science perspective. I think that the current visualization techniques in the field of data science are a little bit biased, right? Because you have to, in general, you select the visualization according to the pattern that you want to see. And it could be a limit sometimes, while the graph enables you the opportunity for not being biased during your analysis of the data, because you see the graph from as an overview, and then you select the direction in which you want to investigate more to discover further details and further patterns in your data. Just a little comment.
Great. Sorry.
I think it's better to take it proactively than being asked for it. Here's a comment about, again, I mean, this is what I feel. This is that I work on multimodal stuff, right? One of my colleagues, I respect him a lot. He's this physics, math kind of background, right? Computer science, but with focus in physics. He says that, look at the data, right? Points, let's say, in the case of math. Now, how do you want to represent it? Do you want to represent it as XYZ coordinates, or do you want to represent it as polar coordinates, right? Depends on what you are trying to prove. If it depends upon your workload, right? I may want to look at it as a polar coordinates if I have to do something which actually is suitable for that representation. It depends upon my workload. Another problem comes up, I want to see it as XYZ coordinate, right? Because it's easier to express. The point is, which one is correct? Nothing is absolutely correct. It depends upon what you are trying to find from there, right? I could have, at the expense of replication, I could have the same data for efficiency purposes, right? So that I don't have to do processing at that time, transformation at that time. I could represent it and store it in two different ways and actually direct it to the right one, depending upon what question you are asking, right? And it also depends upon the user's mental model. What is he more familiar with, right? So that's what matters. So coming back to the thing about relational and graph, right? Visualization, I may keep my data as relational underneath, because relational is a very efficient structure if you want to do set-oriented operations. If you are trying to do a traversal where you are getting sets, large sets in between, right? You want to have that go against a relational representation. But when I'm showing the visualization to the user, right, depending upon the scale, I may want to show it as a graph because he may like that, right? So the user doesn't have to know how I'm representing it inside. He just wants to make sure that I think he's thinking in terms of graphs. He wants to think that the system is also giving him the interface. He wants to see an interface where the system is showing it to us as graph, right? So again, I mean, there's a multi-model aspect here. Which one is good? There's no absolute one representation that is good for everything. It depends upon your problem. It depends upon the perspective of the user, his mental model. So there are many aspects to it, right? That has to be considered.
Awesome, great, thanks, Suri. So we have less than 15 minutes left. I think one topic we also wanted to discuss is adoption, but we also want to open the conversation to the audience. So we will open questions now, and and we'll take it from there. So.
Thank you so much. And thank you for the great panel discussion. It was very insightful. I'm Neha, a PhD candidate from Rensselaer Polytechnic Institute. And I was looking at the different topics that all of you discussed about. Like we also talked about the creating and maintaining KG using graph data science and graph and ML being the future, the rules and how we can enrich and everything. But is there a way, can some of you throw light on how we can actually evaluate what we are doing and not just the quality evaluation that you discussed in between, but the actual graph that we are generating? How can we evaluate that and see that, okay, what we are doing, or can we come up with some tools to make sure what we are doing, how important that is, or how that can be used, or in general, how it can be evaluated? Thank you.
Thank you, Neha. So you don't have to answer all of you, so we can take more questions. So we maybe take a champion, the one who really wants to answer, and we'll go to the next.
Okay, so when I think about evaluating a graph project, right? So I'm building a graph. How do I know if it's successful? One of the things I work with a lot of customers, community users, it's keeping that use case in mind. If someone is like, I'm building a graph because I thought it would be neat, you know, why? Like, what's the question we're trying to answer? So like a great example is fraud detection. I'm going to build a graph. I want to have users and I want to have banking transactions. And the company I work for wants me to find fraud. So I can evaluate my graph in terms of, you know, how big is it? How quickly can I import data? Standard software engineering things. But then the value proposition that you're evaluating it by might be, how much fraud did I find? Or like one customer we work with, their main concern wasn't a dollar value. It was increasing true positives, decreasing false positives, right? And that was their success criteria. And that was really driven by their use case. So their evaluation wasn't, you know, pure math. It was, this is the problem I'm trying to solve. Does this graph that I've built solve this problem? And then continually iterating to improve kind of their own evaluation criteria. So for any project you have, you know, it comes back to the rules of like, what am I trying to do here? And I think that's probably the most important thing when you talk about evaluation.
Can I have a very quick one? Unless you're a genius, nobody can assume you can build the right knowledge graph. That's a trap. So that's why I have to base on actual use case and then figure out how to evolve, because try to avoid that temptation. Because you put in a corner. That's why I always have to be able to evolve based on. That's why real metric. In this case, use case. If you have multiple use cases, metric is the key thing. You cannot say, look at the graph. Is this the best? I don't know. Who can tell? Your view and my view is very different. Right.
Thank you. So let's take a question online. So we have Jacobus Jelok asking, machine learning and rules can enrich the graph. This is great. But what about executable models that implement, for example, a data retention policy or an entitlement calculation policy for executing the logic of a workflow? So what about executable models?
I'm not sure how to answer that question. So maybe you're better at that.
So I can take a stab, which is one advantage of kind of having your data science tied to a database is that your data science workload lives in the same place as your data storage. So one of the things my team worked on and introduced was the concept of a model catalog native to the graph database. So databases are really good at storing stuff. Hey, they can store models too. And so one of the features that we've introduced actually that we'd love to get feedback on is the ability to store that predictive model that you've generated from your graph data natively in your graph database so that it can be called to create those graph updates. So it's executable within that data, the same ecosystem as your data storage.
So if I understand correct, when you say model execution is really about inference, right? Once you build a model, can you actually just apply the model? I totally agree with Ashley. If you have a database, it's just run like a query, right? It's within 10, 40 milliseconds. If you have a new data, that's why we have a feature. You can using Kafka streaming real-time updates. Within that, trigger the actual model execution and streaming the output out. That's the model execution.
I'm sorry, Alicia. Sorry.
Yeah, just adding a bit to that, these answers, the more correct answers, obviously. Yeah, when you have your database, right, is the best place for storing data so that you can retrieve it quickly, right? If you have inferred something, if you have derived some facts, right, store it in the database. It's there. It's basically secure, transactionally correct, and all those things, and your retrieval is fast and scalable. So that's like, extremely important, and you should take advantage of databases when you have them.
Do we have other questions in the room? Yes. You. Where?
Thanks. This is Rajiv with Procter & Gamble. And our problem is like we are more than close to 200 years old company. Okay, we have tons and tons of data. I mean, you won't believe that how much data there exists. So these are old database systems. There are no data models left. Some of these systems are handwritten. Some systems are even Excel. Some are SAP. Some are XYZ. Name the database system, we have it. Okay. There is many times no business knowledge left. Now, how do I build graphs from this? Because for us, we feel that if we have to go into the next generation of the world, like the data science, and apply these models, we will have to get into it. Let me give an example. Let's say chemical, how a surfactant is made, a detergent is made. And that knowledge, yes, exists in people's brain, but there is also chemical knowledge. Chemistry is there. So the mechanisms are effectively graphs. I mean, if you didn't know that they are effectively graphs. So now we're getting into this space that how do I build a graph from all these systems when I have no idea of knowledge? I mean, in the past, we have been doing Bayesian. So for us, the Bayesian was the best approach to do it because EM algorithm exists and I can go through probabilistic methodologies. What is the alternative to Bayesian EM algorithm in the graph world? I mean, Bayesian networks are also graphs, but.
Thank you. And to the list of databases that you listed, we can also add unstructured data, like text data. I'm sure that you also have a lot of.
Unstructured data, these could be purely somebody talking.
Great.
And we can find a retiree who's like 89 years old and he'll be talking about this. So
Good.
think about that.
So who would like to take over?
Let's get to think about Tabular because I know that NLP, I'm not going to exclude NLP pieces here because that information, I can still get it. I'm going to talk about like all these tabulated data that are sitting. I have no data model. I have nothing. I just have these Excel sheets. What do I do?
So one of the things, again, it's not like automatic. It'll happen immediately. So it's not trivial. But we, in the RDF world and in the property graph world, right, we actually provide ways to map your data to a schema, to a graph. Right. So you could actually, I mean, again, it doesn't, the good thing is that it can be a view. So it's not like you're materializing anything. You can actually create some mappings, and then you can, again, because the knowledge is not complete, you don't have the complete idea of the schema, what exactly it represents. You could do it iteratively, right? Bring up something, some portion of it, select a portion of it, map it using just a simple mapping, either using R2RML or using the property graph mapping, which is in the PGQL, it's allowed. I'm sure there are other options also. And that's how you can start viewing it as graph, right? And then you can actually try to see through experts and so on to get some idea. Because again, when you view it as graph, so it becomes easily visualizable. That will give you more insight as to the relationships between the data points there. So I'm saying that that could be a good start for you. So,
I mean, How is that any different than EM algorithm, like expectation maximization in Bayesian word? It does that for you. Why would I do this? Because here I'm involving a human. My Bayesian will take care of that. Why would I do this?
Okay.
Why not?
So I have some deep trauma associated with the use case that you're talking about. In a past life, I used to work for Dow Chemical. And same thing, right? A project I worked on was, we have 120 years of synthesis data, lab notebooks, stuff on old machines. Help. And I'd say the first thing you do is like have a good cry. But then you can kind of take it from two approaches. One is the mathematics approach, and the other is like more of a practical approach. And I'd say from like the pure math approach, you can talk about methods to construct graphs from tabular data, right? I can do k nearest neighbors based on cosine similarity from my Excel spreadsheet, like each row. I've got images, I can embed them, I can create nearest neighbors graphs from those embeddings. I can infer from primary and foreign keys in my table, hey, there's probably a relationship here. But where's the value add? Chucking stuff into a graph doesn't necessarily add value. Maybe I shouldn't say that working for a graph company. So what I would say is like really it comes down to, instead of saying I would like to put everything into a graph, starting from the business problem, like finding a business problem that is improved by a graph. So you had the example of like chemical synthesis. And so we're now not like, don't boil the ocean, let's pick, going back to Dow Chemical, I want to synthesize spinatoram. Okay, I've now decreased the universe of data I'm looking at, and I can start to talk to my SMEs, start with those mathematical techniques, but then have someone who can evaluate it because I'm focusing on a single problem. And I can have that domain knowledge of like, okay, chemical synthesis, what goes in that graph? Raw materials, intermediates, manufacturing facilities, quality assessment data, maybe shipping data. And I start going from boiling the ocean, like I have 200 years of data, help, to I have a very defined problem. I can define the things that should be in my graph. And then when you're using those mathematical techniques, it becomes much simpler to evaluate, like, is this giving me the right answer? Is this useful? And even picking the right mathematical techniques.
Yeah, overall, I agree. There's really no single magic can do everything you want, but it's a combination of everything we just talked about. First, we have to recognize it has to be human assistant. There's no black magic. Second of all, mathematical model only tell you something, but you have to register. You have to capture the result. That itself is knowledge graph. So all we're saying is the knowledge graph tool or graph tool, like property graph, can help you to facilitate that process, right? Whether you use human or machine, but capture the knowledge you discovered into a graph so that you can start enriching the graph, you can modify, you can evolve, and ultimately you will cover the whole world. But that approach can be very incremental. You start with one small use case and then focus on, you can use some of the RDF technology when you interview domain expert. You may even go to the industry domain expert to see what's going on. I think there's a bottom up, tops down, combined with human, machine statistics based, and using the graph technology to unify everything together will get you what you want to do.
So you're telling me there is no AI there, only human.
Well, AI is a combination, right? It's a combination.
So thank you very much for your answers. So we're at time. Giuseppe, I feel like you did not speak too much for the past. Is there?
Last question. I think that the very bad thing to do is, okay, I have this data. I want to create a knowledge graph with all my data. Because as underlined by Alicia and Jay, you have to identify the business case. You have to understand the query that you want to perform and model your data in order to make this query efficient. So basically, this is the initial point, and then you iteratively incorporate the data within your knowledge graph in order to answer another query, in order to create a novel business use case, and etc. So basically, I think that the very bad approach, actually, there is not a unique approach because it depends on the domain, right? But the very bad approach that you can perform is, okay, I have a lot of data, a huge amount of data. That's nice. That's wonderful. I want to create a knowledge graph that resolve all the problems in the world. It doesn't work like that. So.
And we will conclude on that. Thank you very much for this very civilized conversation. It was a great panel.
If you want petabyte level graph, talk to us. We'll be the first company cracking it. 6 months.